So today I'm excited to talk to you about the new project I've been working on with Dr. Geckelman, plasma physicist, and Haley Marks, who's here with us today, who's a bioengineer and amazing microscopist. And I want to give you a little bit of a background narrative. So everything starts at this moment. This is December 13th, 2022, when this nuclear fusion breakthrough happened in the National Livermore Lab, the National Ignition Facility. And some of you may remember it was like a large fanfare around this event. And of course, I was super interested. I started digging about it and thinking about it in relation to what does this exactly mean? Because it's an amazing feat, but is it really for the future of energy, or is it the future of weapons? Like, what are we doing here? So I started digging into a little bit and finding out about these laser bays. Now you have to stay with me just for a second. If you, in your mind, imagine a football field. Now spread that into 3 football fields and then imagine lasers. And these lasers of 3 football fields are directed to one tiny target that's the size of a bead. And that's what results in this so many like mega tiny time of seconds that created this fusion. So here's this machine, and this is the idea right here that you're talking about. The National Ignition Facility lasers compress fusion fuel to exceed 100 billion times Earth's atmosphere and the temperature of more than 100 million Kelvin, which would be 180 million degrees Fahrenheit. So this forces the hydrogen atoms to fuse in this controlled thermonuclear reaction. All this to say that right at the outset, I want to give you a sense of scale and a sense of how we can't even register what's going on. And then to backtrack, and I'm going to show you a little video because it's easier. I have been talking to Walter Geckelman, who's a plasma physicist focused on alpha waves, which are waves that are giving the energy to solar and sun plasma. Since the start, I was working at UCLA and taking my students to his lab, and really his door was always open. And somehow in the back of my head and the back of his head, we were thinking to do something eventually. This wouldn't happen until 15 years later when he was ready to retire. I'm like, okay, let's do something. So I'll give you just a short, let's cut to the chase here. Easier than me talking about.
And we build machines. This is one of the machines we built. It's called a large plasma device. Obviously, it's large. So inside the machine, there's no air. It's about 1/1000th of atmosphere. We inject the gas, and then using electron beams, we tear the gas up and heat it to a temperature of about 250,000 degrees. And you can see through the windows every now and then a flash. That's the plasma. This experiment is studying something called magnetic ropes. The whole sun is completely littered, the surface of the sun. And they actually extend out from the sun far enough away that they sometimes get all the way to the Earth. So it's a sort of solar physics related experiment. Other experiments we do is when there is a large input of energy from the sun, you can get really high energy particles trapped in the Earth's radiation belts.
So I'm trying to get an artificial way to control the Earth's radiation belt. Now every day our life relies on space satellites so much, but they go in and out the radiation belt, and they could be seriously damaged by all the charged particles trapped in the Earth's radiation belt. And so far we haven't had a very effective way to artificially control these charged particles. I'm trying to come up with a way to solve this problem.
So I'll have links to everything I show you clips on. Oops, sorry. This gives you a little bit of a sense of his research that and the background of the NIF breakthrough, right? And talking to Walter again, let's do something finally. And in the following year, 23 of the winter quarter, we decided to put together a Fiat Lux course called Physics and Art Equals Energy. And really, a lot of it was based on the momentum of this kind of breakthrough, where one of his ex-students or collaborators actually was one of the lead people in there. So he had kind of an in, and he immediately said, let's take the students there. And so I got very excited, as you can imagine. We did. We managed to get a handful of students, put them in a van, and we're there for 2 full days. I have absolutely no pictures to show you, of course, because they took our phones and everything. And basically everything is in my mind of what we saw. These images are from what you can get online, and these are things that we saw and the lab facilities we were privileged to view, and it really was incredible. So, but it still left me with, well, I don't know what to do with this, like how do you create a project around this? And I certainly don't want to advertise, these kind of events. I wanted to somehow participate and have it collaborative, of course, because it's art science. So cut to, we start thinking about, when we were going to do the Fiat Lux, I did Fiat Luxes in the past that were related to food, and it was related to the Hawk Zodiac project that some of you may be familiar with. And we actually got some funding for that through a Rothenberg Foundation. It's a food foundation. And so we needed money for doing this excursion. Let me go back to it for a second. And so going to this excursion, of course, we needed the vans, we needed to stay the night, all of that. So I wrote to the Fiat Lux, we needed some funding for this. And because I did 2 Fiat Luxes with food, they assumed this was the same. I think they may have read the email very quickly. So they said, well, we have funds from the Rothenberg Foundation. And so I said, okay, great. Sun food, sunflower. Okay, we can do this. And Walter was like, what? How is this related? It's related. We wouldn't have food without the sun. So that was kind of starting to propel us to think about the fusion energy in the sun in relation to food broadly, and to sunflowers to some degree. So here's something, the reason I wanted to do this lecture, and this kind of total pop-up lecture, is because it's almost like a public service in a way. I feel like people should know what's really going on with this solar flare. And on Wednesday, there was a huge one, which is the X class. So let me show you here really quick. This is from NASA.
On May 14th, 2025, the sun unleashed its most powerful solar flare of the year, a formidable X 2.7 class eruption from sunspot region AR4087. This event caused significant radio blackouts across Europe, Asia, and the Middle East, highlighting the profound impact solar activity can have on our technology-dependent world. In this video, we'll explore the nature of this solar flare, its immediate effects on Earth, and the broader implications for our...
So as I said, I'll give you all the links to everything. I'm not going to keep showing you, but I will show you a few things that, for instance, the main concern in general is this.
Experts warn that AR4087 still holds the potential to release more powerful CMEs, especially as it continues to rotate more directly toward Earth. This rising activity emphasizes the critical need to understand, forecast, and prepare for space weather events. Agencies such as NASA, ESA, and NOAA's Space Weather Prediction Center have intensified monitoring of solar behavior using space-based observatories like the Solar Dynamics Observatory, SDO, and the Parker Solar Probe. These missions are designed not only to observe the sun's outer atmosphere, but to help scientists predict solar flare patterns and alert Earth in advance of any dangerous CME impact. While solar flares themselves strike Earth almost instantaneously, traveling at the speed of light, CMEs take longer, typically several hours to days. This delay provides a crucial window for early warning systems to alert satellite operators, airlines, and grid managers. However, not all flares are accompanied by CMEs, and not all CMEs are Earth-directed. Predicting them still remains one of space weather forecasting's most complex challenges.
So basically, they can predict up to a day ahead, which is like wonderful. So then the question is, when you see a lot of these research kind of directives are about satellite systems. I mean, if you think about how many satellites are now going around the Earth and their whole infrastructure based on it, it's pretty intense. So we have another quick clip.
In September 1859, scientists observed the first confirmed powerful solar flare. The sun threw a large amount of radiation, energy, and plasma material into space. This was a massive and devastating disaster, but it happened 93 million miles away, so it probably wasn't such a big problem, right? Well, actually it was. A few hours after the flare was spotted, telegraph lines stopped working all over Europe and North America. Some of them sparked and caused fires. People realized that the sun was not only the source of light and warmth, but also danger. Scientists called that day the Carrington effect. The good news is that this happened in the middle of the 19th century and didn't cause serious problems for the planet. The bad news is that scientists are warning that in 2025, Earth will experience even more powerful solar storms caused by a coronal mass ejection. This is a giant cloud of plasma or charged gas. At one time, the sun can throw billions of tons of this material into space. Then, all this flies at high speed through space. Some of the material can reach our planet in 15 hours, the rest in a few days. During the journey, it captures and accelerates any charged particles encountered along the way, which increases its intensity and power. And then, this unstoppable array of energy crashes into our planet. It heats the upper layers of the atmosphere, increases its thickness, and disturbs the work of satellites. They slow down and lose altitude. Communication with satellites becomes unstable. GPS is buggy. Data is poorly transmitted. Also, solar charged gas penetrates into our power grids, transformer booths, and stations. It leads to massive failures that ruin the work of the entire technological chain. A powerful solar attack on several power plants can trigger a power outage in a large city. The internet, phones, social services, networks, nothing will work. We may lose connection with each other. Many large companies would go bankrupt, and the planet may face economic crises. These are big problems, but not the most serious ones. Electric plants serve boiler houses and water pumping stations.
So you get the idea. I'm not going to go further into it because, again, I'll give you links, but you get the point. And of course, very little is mentioned about the effect on humans, which I think is really interesting to think about it and to think about in relation to all the research. So just for the talk to go with some vocabulary here, there's this a way of measuring the flares that happen to us. So ABC are considered small, M is moderate, and X is the strongest. So when you hear people saying there was an X flare, that's what it means. And that's what happened just last week. So these are the sunspots. And this one is really huge. And that's where those enormous flares come from. Here's a close-up image of them. It looks amazing. And then this is how it's measured. So it's measured by looking at the count of the sunspots, and the dark spots indicate activity. And then there's CMEs, which a lot of people can say, oh, it's a CME. That's coronal mass ejection. So that's like when it's giant clouds of charged particles are going off. And then there's the geomagnetic storms, which actually it's the Earth, magnetic fields of the Earth responding to it. So again, you saw a little bit about the Carrington event. That was actually super interesting because it happened at a time where there was very little electrical infrastructure. And this is the notice from the newspapers about the auroras. So you heard about last year, there were a lot of aurora displays. That's part of it. It's because our sun is really going wild. So it was talking about how they were so bright that you could read at night, and it was so regular that you didn't even have to use batteries. The electricity was so extraordinary. He made this drawing of the sunspots, and that's one of the earliest researches, again, to show how scientists are artists too. And then this is an interesting research done in Europe. It's called CubeSat. It actually goes close to the sun and measures the solar storms. Our look at the Earth and how fragile we are with all our satellite systems, and then how it affects our magnetic field. I asked Walter actually how big is the Earth compared to the sun, and he said that the sun is diameter is 10,000 times bigger than the Earth. So you can kind of see how small we are in the scheme of things. All right, so this is again to show you just how it's all measured, looking into the particles, the storms, the solar winds. And what we talked about earlier, this is how it's usually looked at, ABC, and then X, which is where we are. So now let's look at how it affects the Earth in relation to climate change. In other words, with fossil fuels and all what we're doing to the Earth, it's literally like throwing oil into the pan. I mean, it's just really like throwing oil into the fire. So this is a picture from a recent fire here in LA. And then looking at the fires last month in the country and then in Mexico, and then expanding out to the world. So this is all from last month. So we're not talking, a lot of times everybody's focused on LA, and I feel like, okay, yes, LA is burning definitely, but also everywhere around the world. If you look at this map, this is what was measured last month. And then that, of course, ignites floods. So this is, again, floods all around the world. And that brings me to, well, what about our bodies? And this is the person that I find absolutely fascinating. I will also link to his paper. Alexander Chizhevsky was a scientist from Russia in the 20s. Super intellectual, super active. He was also at the United Nations. He came to New York. He was very active. And he was one of the first people that actually started paying attention to the solar flares in relation to human behavior. So this research that he did was he took it to a very, very broad and incredibly ambitious effort. In other words, he thought of making a history of humanity based on solar maximum and what happens during that. So he went all the way from 500 BC to when he was alive. You can see here in 1922. And he was looking at the history and how it relates to repression, to the masses, etc. And guess what? Stalin did not like this research, and he threw him into the gulag. And so the poor man was in the gulag for a while, and then somehow his research did not continue in that direction. But he found that 80% of the most significant events actually happen during the maximum activity. So here's a short clip I want to show you. All these people.
As we go about our daily lives, we aren't generally aware of the forces generated by solar activity or the Earth's magnetic field. While these planetary changes are well documented, precisely how they affect human beings is less clear. To answer this question, researchers have turned to the autonomic nervous system, the subconscious control system that regulates bodily functions such as breathing and digestion. Their findings suggest that our nervous systems are well attuned to the energetic fluctuations that ripple through our solar system. The work builds on observations made by the famed astronomer Alexander Chuchevsky during World War I. He noted that battles intensify during peak solar flare periods, and that major human events and behaviours closely follow the cycle of the sun, which led to the hypothesis that some unknown solar forces affect human health and behaviour, providing a provocative link between events occurring in our solar system and life on Earth. To test this hypothesis scientifically, the team looked at how the human nervous system responds to changes in solar and cosmic radiation, as well as in the Earth's magnetic field. They accomplished this by focusing on heart rate variability, an indicator of autonomic nervous system function. This variability was tracked in 16 women, who wore heart rate monitors for 72 hours per week for 5 months. The data were then compared to changes in cosmic rays as well as geomagnetic and solar activity occurring over the same period. The team found that heart rate variability significantly correlated to variations in 3 key variables: cosmic rays, solar activity, and Schumann resonances. Strikingly, the participants' heart rate variability rose in response to increases in these variables, and the response was quite rapid. These positive correlations suggest that human physiology reacts favourably to these forces, supporting Chuchevsky's hypothesis that environmental factors can act as energy sources that affect health, mood, and behaviour. Although the full importance of these relationships isn't currently known, the findings suggest that cosmic and solar energy don't just change Earth's magnetic field, they also affect human physiology. The work also poses the intriguing suggestion that some aspects of these energies might subconsciously connect human beings across the world.
And so, to some of us, it seems logical, right? That if it's affecting the whole planet, it may affect us. But let's take a look at the wars that are going on currently. So we have 10 active wars on almost every continent, okay? And then we have the fires, which I showed you repeatedly. This is the most recent. We're actually worried here in California again. And then here's the floods and the climate disruptions. And so here we have some more research that's coming up. And this is from the Solar News Network, the Space News Network, which I thought was very cool that they actually looked into it finally.
Welcome back to Space Weather News, your daily source for all things space weather related. If you enjoy our videos,
let's go here. I'll skip it. Again, you're going to have all these links. So let's start here.
Solar radiation can penetrate the Earth's atmosphere, causing a range of health effects. One of the most significant health effects of a high KP index is an increase in the risk of cardiovascular disease. Solar storms can cause a surge in geomagnetic activity, which can lead to changes in the Earth's magnetic field. These changes can cause changes in the human heart rate and blood pressure, which can increase the risk of heart disease. Studies have shown that during a high KP index, the incidence of heart attacks and strokes can increase by up to 30%. Another health effect of a high KP index is an increase in the risk of mental health disorders. Solar storms can cause changes in the Earth's magnetic field, which can affect the human brain's function. Studies have shown that during a high KP index, the incidence of depression, anxiety, and other mental health disorders can increase. This effect is thought to be caused by changes in the brain's production of serotonin, a neurotransmitter that plays a crucial role in mood regulation. Solar storms can also have an impact on the immune system, increasing the risk of infection and disease. During a high KP index, the Earth's magnetic field can become unstable, allowing solar radiation to penetrate the Earth's atmosphere. This radiation can damage DNA and weaken the immune system, making it more susceptible to infection and disease. In addition to these health effects, a high KP index can also have an impact on sleep patterns. Studies have shown that during a high KP index, people tend to experience more disturbed sleep and insomnia. This effect is thought to be caused by changes in the Earth's magnetic field, which can disrupt the production of melatonin, a hormone that regulates sleep patterns. Overall, the health effects of solar storms and high KP indexes are significant and can have long-lasting impacts on human health.
All right, so we're talking about our bodies some more.
Welcome.
Oops. And so what they're starting to feel, and this is also published in journal Nature, is that there's psychological effects, brain activity changes, as you saw in a couple of these clips, blood pressure changes, and it really affects pilots and astronauts and, of course, planes. You've noticed that there's been quite a few disruptions in news around planes. So yes, a lot of times the reason is because of people have been laid off or the infrastructure is down, but even this is connected. So it's there's no black and white answer here, but for sure it's everything that's there is amplified. And this includes, of course, animals too. So there's disruption to bird migrations, and animals, of course, feel much more than us. So that brings us to sunflowers. So how did the sunflowers come into the picture? Of course, they're the symbol of the sun, but they're also incredibly complex. And we started really looking into it as on many levels. So starting with the head of the sunflower, each sunflower is made of smaller sunflowers. So the petals, we see they're not the ones, the florists are like every one of them is a sunflower. So each one of these is actually a full-on sunflower potential. This is a close-up. It is its food source. So it's basically the seed is the food source. And this pattern is a Fibonacci pattern. It creates oil, of course, and the biggest producers of sunflower oil are, guess what? Ukraine and Russia. And who are the biggest countries that are receivers of this oil? Guess what? It's China. So does it get affected with politics? Yes, because the largest producers can't easily export to China and India. So you suddenly have a huge influence of these disruptions in agricultural activities that include sunflower cultivation and processing. So then there's the idea of seed. Actually, I talked to Walter Geckelman about this as well, where you think about the target of the NIF that I started the talk with, and you think of the seed of a sunflower and how complex that is and what it grows into. So we have this idea of connecting, the idea of target ignition and fusion, and the growth of a sunflower seed that releases energy and emergence of complexity in a different way. That seems simple. It seems like less complex than what is being done in nuclear physics, but I'm actually saying it's not, because if you start looking at the complexity in the global sense, it's pretty amazing. This is sunflower field, and these are all the sunflower seeds that are sitting in hangars and cannot be used because of transportation problems. And the most amazing part that maybe some of you are not aware of is that sunflowers are actually used and were planted in Chernobyl and Fukushima, where the disasters, nuclear disasters happen, because they actually absorb the toxicity, the radioactive toxins, which again is pretty amazing and brings us back into the connection, which may seem far-flung at first, but it seemed more and more obvious. And then, of course, the seed of the sunflower gives us so much to work with and think about in its formation. It makes us think of form and all kinds of complexities. I can't even verbalize. There's so much going on. There's also the idea of color. So the yellow, it also holds an ultraviolet pattern, which is invisible to most humans, but not to Haley, who's going to talk in a minute, where we have patterns like what's behind me is actually going into the deep into the sunflower. And these molecules that are found in sunflowers produce UV patterns that also help the plants survive the stresses of drought or extreme temperatures. Health-wise, it's so the kind of opposite to all the stuff that we're being hit with the solar flares. It's actually very good for your heart. And it's got everything that can help your immune system, your skin. It's got magnesium. It's very good for the heart of all things. And so that's how we started even looking at this is the question that Walter kept asking me, well, what's sunflower got to do with plasma? So we started thinking about it and thinking about the process of photosynthesis and how complex that conversion of sunlight into chemical energy is and how it's captured. It actually is mimicking in a way what scientists are trying to mimic. And then it's used, cold plasma is actually used in food systems. So we did come around to how is it related to actual science. It's used in seed treatment by disinfecting the surface of seeds. It's for disinfection. It can also be used for water purification. It helps promote plant growth. And a lot of it is without chemicals. So it's actually got potential for large agri. So we did a little experiment. What you see here are 8 or 9 pots where we planted a seed of sunflower in each one. And we grew it, we treated them with different times of plasma. So going from 10 seconds, 20, so on. 2 minutes was the longest, and 2 minutes did the best. And it didn't, and the one that wasn't treated at all did okay. So I don't know what we decided on that, but it was showing that it made some difference. Here they are growing on the physics patio and fully growing during the summer. And then it went into the lab. Here it is getting dry, and we had our first customer. The squirrels found the seeds, which was very lovely, right in the physics building. So now I'm gonna hope that I can pass it on to Haley. Haley, are you still around? Great, yay.
Yes.
So I'll stop sharing
Good.
and I'll let you take it on. So everybody, this is Haley Marks. She's a microscopist, bioengineer. She works at the California NanoSystems Institute in the basement. And we have been, last couple of years before that, we were showing students around, and she has access to the most amazing and powerful microscopes. So advanced light microscopy and spectroscopy laboratory at CNSI. Thank you for coming along, Haley.
Alrighty, so we're going to start with a little bit of Sunflower 101, which you kind of already went through, but just so you know, some of the terms I'm going to use when I show the images. So sunflowers are actually hermaphrodites, meaning that they can self-pollinate. but they're more likely to self-pollinate with the help of bees. So when we zoom in on the flower, right? Right, so cross-pollination isn't occurring, right? If the sunflower is a hermaphrodite, why does it need a bee? How does it pollinate itself? So it can pollinate itself just like without a bee, but it only has about a 2% success rate because they need the bees to basically crawl all over the florets, which are the tiny little flowers that Victoria mentioned earlier, coming out of each seed. So they expedite this pollination process, making sure that it happens early enough in the year. So waiting for it to happen naturally would be too slow. And then they also can stick onto the edges. And the way that they can see where to go is by the fluorescence. So what I'm going to show you is more like what a bee sees than it is like what you see. And you can see up in the top image what Victoria was talking about, how each one can be a flower. This is if you let a sunflower kind of go wild, like more flowers will come out of its center. And there's the bees crawling around them. All right, so what I'm going to zoom in on right now, right, is this entire floret. So where the top little piece right there sticking out, there's like another little smaller looking plant coming out of the middle. That's the stigma coming out of the style, or the anther, depending on how low you're going. And then the bract is that kind of that small spiky leaf that holds the bottom of each floret. So if we look at this under the microscope, right, this is what it would look like to your normal eye under using a normal microscope. This is 10x magnification through the eyepiece and 10x through the lens. So about 100 times magnification, zoomed in on one of these, plucked out and laid on its side. The bubbles you see there are because we put it in a glycerin solution just to keep it fresh for a long time. And then now if I show you on the left, this is what it looks like under fluorescence. So this is showing the autofluorescence, so where I shine UV light and I see back the excited fluorescence image coming back at the camera with a special set of filters. So if you look in the bottom right of the image, you can see where where's my mouse? Right here, you can see where it's very red in this part of the image. Over here, you can see this is the leaf, right? So that's the chlorophyll in the leaf and the green part of the leaf right there of that little part of the bract sticking out. You can see there's green autofluorescence going through the middle, and then there's an even brighter green autofluorescence coming right here. And then you can see if we zoom in on this little guy, that was actually a little invader bug that got trapped on the floret and in our imaging solution. But he has a slightly different autofluorescence profile, and that's because everything chemically has some small amount of autofluorescence in the plant, right? So each of these molecules inside the plant has its own unique color, and we can isolate this color with our fancy microscope, which can separate each band individually. So if we think about, where's my next slide? You versus our microscopes down here in the basement at CNSI. Your human spectral vision limit is about 800 nanometers. So that's like maybe a third of a human hair. Your human vision resolution limit, well, I guess 100 microns is about your vision, sorry, 100 microns is your human hair vision limit. The spectral limit is going to be 3 bins, right? So red, green, and blue, like you see the way we design cameras to see, which is with red, green, and blue pixels. If we think about the size of a single neuron is around 15 microns, right? Compared to our vision. So that's much smaller than our vision. It would just look like one blurry pixel. And your camera phone's resolution limit is around 1 micron. So it's about 100 times better than our vision, but still only 15 times smaller than, so it'd still only be 15 pixels wide for a neuron. The current normal light microscope resolution limit is about 100 nanometers or 0.1 microns. And with our super resolution light microscopes, or with the latest MinFlux super resolution light microscope, you can get down to about 1 nanometer right now with light. In terms of video imaging speed, if you want to think about how long it just takes you as a human being to process an image, like to interpret something and respond to it, it's about 13 microseconds, where your neurons are firing about 1 to 30 neurons per second. Your normal video, speed is going to be 30 to 60 frames per second, where our light microscope imaging speeds are going to be like 2000 frames per second, so much faster than you can see. So we're imaging things that would normally not be perceivable for you to look at through the microscope lens with your eye. We have to have a very special fancy camera setup for that. But it wasn't always like this. Back in the day, people used to do, specifically Santiago Cajal, who is kind of the father of modern neuroscience. And part of the reason he has that title is because he, with only a flame and an old microscope, since electricity wasn't invented until he was in his 30s, sketched by hand all these neuron structures. And that's the basis for how we know what neurons look like today. And even in our lab here, actually, when I cleaned out my office from the person who had the job before me for, I think, 50 years here at UCLA, I found physical film in the drawers of the lab from back
Oh,
when microscopy
wow.
used to have physical film. We used to have to
That's
take it and then
amazing.
process it in a photography lab. So microscopy and photography used to be very closely connected. And
Very
yeah, it was very
cool.
fun to find all the rules of film, wheels of film in the lab. Okay. So if I go to there we go. So now we have this, the phone in your pocket is actually pretty incredible. So these images are just taken with like a standard, I have a Google Pixel 6a, so not even the latest, nicest phone. And you can get pretty high quality macro lens type photography images just with your phone camera and a nice steady like tripod or zoom stabilizer. And it's actually quite impressive where we've come today. This used to be like kind of the standard for stereo microscopy and is now something that everyone can kind of just carry around. So with like just one little extra lens or two, you can turn your phone into a microscope pretty easily as well. Yeah, let me go to the next slide. Yeah, oh, sorry, it's so loud. It's not kind of showing what, yeah. So now if we go one step up from the phone in your pocket or a very nice DSLR photography type camera, we go to stereo microscopy. So this is going to be a lot like photography, right? It's like you have kind of like a camera on a tripod like you would in like movie making type equipment where you can roll this whole camera up and down on this base. You can adjust the little lighting arms that are sticking out and have, the lighting coming from all directions, adjust the lighting from the top. And the images you get are something like this. So they're going in a little bit more than what your phone can do, right? Or I mean, quite a bit more than what your phone can do. But there still becomes a point, if you notice when I'm zooming in, where everything in the background just becomes blurrier and blurrier, right? And that's because my depth of field is getting smaller and smaller as I zoom in. So if we want to zoom in even more than this, what can we do? So this is now just to put into perspective what we're zooming in on here on the right side. This is one of those, the smaller little plant coming out of one floret on the right. And we're going to zoom in even more on this. I go one more slide. Yeah, so now if we go to a wide field microscope, so now we're using a camera and a filter and a lens system, and we're having to focus on single planes at a time. And you can kind of see how even though we're able to zoom in more, it becomes more and more difficult to focus, right? It's becoming harder and harder to zoom in without losing that depth of frame. So same thing over here on the left. And this is where Victoria started noticing like, wow, that looks like the surface of the sun. Despite it being, now we're looking at the bract of the flower. So this is the side, this fuzzy little bit of the leaf on the side here.
Mhm.
Okay, so here's that again, looking at the bract, looking at that little bract on there. So just showing you what the depth of field is. So like as I focus, you can see I'm only seeing like maybe a few hundred microns worth of depth at a time. And so what we can do with these images is we can do a technique that's called extended depth of field, where you basically take a Z-stack. So you take every focus possible, and then you can merge them into one flat frame. And so I'll show an example of that here. So here would be something where we panned through and we had all the different focuses shown on the left, and then on the right is the extended depth of field image. So this is the one that's stacked. So same thing here. This is the image that's on Victoria's background. So if you watch the focal map on the left, so this is what it actually looks like when you're looking through the microscope and you set up the stage to move at very specific step sizes, right? Scanning through so the focus is changing, kind of like asking, if you were a photographer, asking your subject to slowly take one step towards you, one step towards you, one step towards you, and then continuing to stay the same image and then stacking on top of each other. If you watch Severance, that's kind of how they make the Severance like warp in the elevator, is they're just changing the lens and having the person stay the same distance, but changing the focal depth. So you're getting a slightly different part of the face in focus every time. And then on the right, this is the extended depth of field image where we stack all those focuses together into a single flat image. So that's how you get that type of high resolution, high zoom image. And this is also, I forgot to mention, this is polarization overlaid with fluorescence. So we're seeing both the polarization component, which is highlighting the starch. So the little shiny dots that you see throughout the plant are the starch, little balls of starch. And then the orange color map is coming from the fluorescence. And yeah, we can also create like 3D maps since we know what the Z position of every frame was on this microscope. So we know where each of these oh, I think it stopped moving. We know where each of these Z frames was taken. So we can kind of make a 3D map, but it's still kind of like a two-dimensional render of something in 3D and not truly something in 3D. So if we want to make something that is truly 3D, what we need is another level up of microscope, which is our confocal microscope. So what we do here is just like if you imagine the microscope as having like near or far-sightedness, we put a little pinhole in front of the detector, so in front of the camera, or if you want to think about it like putting a little narrow set of glasses in front of the person's eye, and that would block all of the near or far-sighted out of focus light. And so instead of having this be your light focusing through your sample, this is what the light focusing through your sample looks like. So you're only illuminating one Z plane at a time or one slice at a time. So if this would be the image of a fish on the top part, so it's very opaque, right? It's a fish, it's a 3D object, right? With a lot of depth, and it gets really opaque wherever it's thicker. With confocal, I'm looking at just one slice, like the way you would on a CT or an MRI, just looking at one thin section of it. And I can, again, move my stage in different Z steps and then build a 3D image from that. So if we look at this same sample, but with the confocal, okay, so this is what the image, taking this image would look like on the confocal, right? So now I don't see anything that's out of focus. I only see one very, very thin plane at a time. But then when I stack this image all together, then I get that render of everything in 2D. Or if I want to zoom in again on one of these little stigmas, which is where the pollen was. So again, inside this little one floret within the sunflower seed, there's this little part sticking out. That's where the pollen gathers on these little spiky bits. So here it is on the left with the phone camera in your pocket, in the middle with the stereo microscope. So that's like the photography style one. On the right with the wide field fluorescence and polarization microscope. And then if we go last to the confocal stack, this is what the confocal image looks like. And you can see its actual dimensions in 3D. So these parts sticking out in 3D, you could measure them and get the correct size of everything and have a full 3D render. So this is where we're going like, you know, from a $10,000 microscope to like $1 million microscope in order to get from that 2D to 3D range. And all of this pigment or all of the color contrast here is just the natural pigments from within the plant, just from color channels that we don't see very well.
That's right. And these are the ones we ended up using in the project. And many of the images, really, if I told you it was the surface of the sun, you would believe me, including the one behind me. I think even Haley, you were surprised when we started seeing the internal structure of these flowers that we see as yellow and, you know, beautiful flowers, but then you go deeper and deeper into it, and it's just amazing. So, all right, well, I'll continue then to show you how all of this connects. If you stop sharing, I'll start.
I think I did.
Yeah, so this is where, thank you so much. And I think that everybody can see and admire how amazing this work is, and also how Haley has been so involved. So we're just continuing because we love it. We also, working with sunflowers, of course, brought us to the bees because they're more than pollinators. They're essential to our food systems. As some of you know, they had some hive problems, and this may be also due to all the different communication, technological and pesticides used, air pollution, all these environmental stressors, right? So they're also navigators of magnetic fields. So these solar storms also affect their movement. And I just got this from Haley the other day. She found it and it made perfect sense. So I'm going to show you like a real small clip
One
of
night I
this. You hear the sound okay? Do you hear the sound okay?
To Earth's orbit, it interacts with the Earth's magnetic field.
I'm a guest, in this world. I'm a guest in their house. I'm a house guest.
I met with Brian, the lead beekeeper from Bees in the D, to find out how bees use electricity in their everyday life.
So we are on top of the convention center, now called Huntington Place, formerly Cobo. And off to my left here are one that I'm sitting on and 3 more hives, honeybee hives. So there's been a lot of studies that show that bees, while they're flying, can build up that static electricity, and the flowers now are cued onto that. And so if the flower is rich in nectar and pollen, it actually communicates with the bees, and it pulls using that static electricity towards the bee, so the bee's hair lets it know that this flower is rich. If the flower had just been visited, or a bee or something else has already used up most of the nectar, the flower no longer does that, so the bee will just pass it by. Bees, they've discovered, have like granules of iron in their abdomen, and that iron reacts to the electromagnetic fields of the Earth.
The way we navigate through the world using sights and sounds, bees use electricity and magnetism that can be affected from outer space.
The disturbances are there. They're fairly common, and they do affect animals.
When Earth's magnetism is disturbed during large storms, bees are less likely to find their way back to their hives. Bees experience a vastly different world than we do. Electricity pulling on them from flowers, seeing invisible forces of magnetism created at the center of the Earth, storms on the surface of the sun creating confusion in their navigation. Bees navigate a world of cosmic disturbances, such an amazing connection hidden in plain sight. Just trying to shift your perspective to the creatures we see all around us all the time could be a deeper dive into the surreal than we could have ever imagined.
So another cool clip. Thank you, Haley, for that. And now I just want to show you how all of this came together. So the sound is actually 8 channels. It's solar wind from NASA's Barker Solar Probe, plasma data that's sonified from the Geckelmann's Large Plasma Device, field recordings of beehives in Croatia, footsteps working along plasma machine, footsteps going along sunflower fields, crackling of fire, underwater acoustics, and spoken word of scientists about these huge things. So here's a 3-minute video that I'll voice over so you can kind of get a sense of it quickly. And now you can actually put together what we've been seeing. So this is kind of our main image. This is where the whole story begins, with the National Ignition Facility announcing nuclear breakthrough. Dr. Geckelmann and his lab. This is a tokamak in his lab. And then the large plasma device that's dedicated to what you saw earlier when he was discussing it, creating these plasma waves to see how they function and how they can be used not only for research, but also for semiconductor industry. They work with them quite a bit, actually. So these videos of walking along this machine is juxtaposed with videos of walking along sunflower fields. So you can kind of get a sense of the space and the class that we taught together, which I already mentioned. So this was when we did research and discussion with the students and also experimented with the sunflower seeds. When I was in Croatia, I went to the sunflower fields kind of to get a sense of it. These are sunflowers going into physics lab. These are sunflowers going into the microscopy lab. And here's Haley dissecting and actually teaching me. She was training me on how to understand what's going on all the different devices. I just became more of an admirer than a practitioner because it's incredibly complex. Here's the field in Croatia that I was passing around. And really, this is when I zoomed onto the bees. I went to a local beekeeper and worked with them as well, talking to them about how bees function. And you saw in the earlier slide, I didn't have any cover because he said, I'm peaceful, so I can go, I don't need to be covered. And finally, the first iteration of the project at Governor's Island. These objects are actually objects, they're from the machine. So they were shields inside of the plasma. And that kind of gives you a good overview. So you have also the sunflower website, sunflower plasma website. And just to end by saying what sound was surrounding us as Schumann resonance, solar wind, fire crackling, the plasma machine, Geckelman talking. By the way, this is a microscopic view of the beehive, underwater drone, and the machine data.